because the first talk, in fact, I didn't prepare on transparency, and it will be very simple thing, which has something to do with dark energy. And it's a paper which I wrote perhaps 1 week ago together with Ali Shamsidin, because we tried to solve cosmological constant problem in a certain extent, but instead of that, we solved, up to a certain extent, again, dark matter problem. And the thing is the following. There was a lot of efforts. I will use blackboard. Okay, so...
Oh, we can't see it here yet.
I can give you also file.
Okay, we just have to switch it from here.
I see. So there was a lot of efforts to solve a cosmological constant problem in a way when you can get it as integration constant modifying Einstein equation. But normally what people try to do in this case, they were considering, for instance, unimodular gravity, and the main idea of this thing was to get rid of 1 of 10 Einstein equation, namely from trace equations. This we don't need at the moment, okay? But I will continue after that. So now, you know that, okay, the talk will be at the level of elementary school, of course, assuming that kids in this elementary school studied general relativity, yeah? So the question is, how can you modify Einstein equation in such a way that you will T alpha beta, and I will use units where 8pg is equal 1, where you will lose trace of these equations. In principle, if you would lose equation for trace, you could rewrite this equation as 1 divided by 4 here, and also subtract 1 over 4, I guess delta alpha beta t. But then you have to supplement something to this equation, and namely, okay, people were writing this unimodular gravity where they were getting, okay, extra solutions which was containing cosmological term as a constant of integration. But of course, when you are losing one of the Einstein equation, it means that you have to implement some symmetry which should be related with some kind of scale invariance, or better to say Weil invariance. And then we tried to do this thing. And namely, we started with separating of the scale factor from the metric. You can write metric, physical metric, in the following artificial way, introducing scalar field. It would be d tilde gamma beta, then d gamma, some new scalar field, d beta, some new scalar field, and then multiplied by g tilde alpha beta. You see, this is auxiliary metric, and in principle, this metric we have to consider as a physical metric, but this metric we will consider as some kind of auxiliary metric in variation principle of the normal action, okay, which gives you Einstein gravity plus, okay, metal Lagrangian, which also depends on G. So now what can you do? You can take this ansatz, substitute, consider the metric, physical metric, as the function of the new metric and phi, and make variation with respect to g tilde and phi. And then what you are getting, you are really getting modified Einstein equations which have extra degree of freedom. First of all, notice that if you would take physical metric g alpha beta, and then multiplied by the derivative of the scalar field, d beta phi, then, okay, from this formula, it's obvious that this factor, when you are raising indices, it will go down. When you contract the things, okay, you will get the same impression, and therefore, just from this definition, it follows that this scalar field, which I have introduced, satisfies this normalization condition, always. Now, when you will vary action, Einstein action, with respect to this auxiliary metric, then you are getting modified Einstein equations, which would look like following. G alpha beta, where G alpha beta is normal Einstein tensor, delta alpha beta A, and then here minus G minus T, where G is the trace of this Einstein tensor, d alpha phi, d beta phi. And it will be equal t alpha beta. So you see, what we got as a result of this modification of the variation principle, consistent change of the Einstein equation, where they appeared this extra term. Moreover, if you would take trace of this equation, then you get that it's g minus t multiplied by 1 minus d alpha phi is equal to 0. You see, previously, before, when we didn't have this modification, of course, when you take trace of the Einstein equations, then you are getting that g minus t is automatically equal to 0. But in this case, because of these normalization conditions, this term is equal to 0, and g minus t is not obliged to be equal 0. Now, to understand what does it mean, this modification of the Einstein equation, take this thing in the right-hand side and write energy momentum tensor for hydrodynamical fluid. You remember what it was? Epsilon plus p, u alpha, u beta, minus p delta alpha beta. And now see the potential motions of the fluid, which means that, okay, for velocity can be written down as the gradient of some scalar field. Then you see, first of all, u alpha, if you would take for velocity, of course, should satisfy conditions that it's equal 1, but you know that, okay, this condition is satisfied if this phi is considered as the potential for the gradient motions of some fluid. Second thing, to get this term, you see that you have to identify pressure with 0, and energy density should be g minus t, which is, okay, in the absence of normal matter, is equal minus curvature. Therefore, from this consideration, you see immediately that this extra term, which appeared in Einstein equations, in fact, imitate completely dust. There is absolutely no difference in the sense of behavior. You can take Einstein equations, okay, in this form, solve them, and then you will get Friedman solution without any matter, but okay, it will be like dust-dominated universe. You can get Tolman solution. Even perturbation here behave completely identically to what you would have in a case of cold dark matter. So in such a way, you are getting just modifying Einstein equation, imitator of dust, or you are getting dusty universe without dust, better to say. Then, okay, the amount of this kind of so-called imitator of dark matter is determined by extra constant of integration, which appears here because all Einstein solutions, of course, all Einstein solutions, but plus there appears longitudinal perturbations, which imitate precisely the behavior of the matter, including gravitational instability. The things which we didn't check, of course, because it's a lot of work. What will happen when, for instance, cold dark matter will form multi-stream flows, so cusps? I'm not very sure that here you will get the same cusps, but might be you can get these cusps. The second problem which appeared in this consideration is the following. I started to think that, okay, if we have inflationary universe, and if constant of integrations are fixed before the beginning of the inflation, then the amount of this dust, better to say dust-like matter, is diluted on inflationary stage momentarily. So because it goes down, I think this g minus t will go down like 1 over a cubed. But then I discovered how to save this model against this problem. For that, you have to introduce the coupling of this phi, which I said, yeah, here, the potential for these so-called velocities, with some function of inflaton field. Then there is no derivative. Also pay attention that this field phi is not dynamical. It's never 0 because it satisfies this kind of condition. And then on inflation, if there is this coupling term, equation for g minus t becomes like this one, g minus t time derivative plus 3h g minus t and is equal this function which depends on inflaton. Now, obvious solution of this equation, because h on inflation is approximately constant, inflaton is practically doesn't change. Okay, it's also approximately constant. Then obvious solution of this equation is that G minus T, which is nothing more than just energy density of this dust imitating curvature, is equal minus this function f, which depends on f inflaton, divided by 3h. So this is approximately constant, and taking function of inflaton, okay, what you want, if you want to get 20 orders of magnitude less of this energy density, then you are getting, okay, precisely what you need to imitate dust in our universe, called dark matter. Moreover, because you see here that perturbation of this thing is proportional to the perturbations of the inflaton, you are getting precisely adiabatic perturbation in a sense in which you would get it for cold dark matter. So, and the question for you, with which I finish this first part of the talk, how to distinguish this thing from real cold dark matter, because this kind of imitator of dark matter will not participate in any other interactions besides of the gravitational interactions, and therefore what Starobinsky says that we are guaranteed that we will find cold dark matter is not so obvious. Okay, so this is conclusion of my first talk. Now I go to the second talk. And second talk, in fact, I gave already at Planck meeting, and this is perpendicular somehow in ideology to what people were discussing today in the morning. Because actually it's infinitely long discussion up to what extent the theory should be fundamental. Yeah? But I hope that there are no fundamentalists in this auditorium, therefore I will try to be not fundamental, but, okay, I will try to relate so-called what people see with observation, not to fundamental particle physics, but effectively to the gravitational part of the story, which actually here is dominating. What in fact is inflation? Forget about thousands of scenarios, which is actually very difficult not just to memorize, even to classify. Everything what we need for making universe like we see today is the stage of earlier cosmic acceleration, because we are considering, in fact, huge scales, in spite of the fact that they are microscopical, they nevertheless encompass many particles. Matter in these scales could be described in terms of the effective equation of state, where the whole matter in the appropriate scales are characterized by energy density, epsilon, pressure, and in fact, everything what you need for inflation, you need the change of the quantity epsilon plus p over epsilon, which should be different from 0 because you want to have graceful exit there, from small value of the order of 10 minus 2 to the value of the order of 1. Because to get epsilon plus p over epsilon of the order of 1, we need, because we want to finish this stage of accelerated expansion. Now, I was thinking for a very long time how to parameterize this kind of equation of state, and I tried normally pressure as a function of epsilon. But you know that if you will take some kind of different inflationary scenarios, then you will find that all these functions are ugly when you try to do it, p as a function of epsilon. But much nicer way is to use the number of e-faults before the end of the inflation to parameterize deviation of the equation of state from cosmological constant. You can write it as a function of the number of e-faults till the end of the inflation. Here, AF is scale factor at the end of the inflation, and exponent minus n, okay, just tell you at which stage of inflation you will. What is relevant for observation normally is only last 70 e-faults. So it's not so huge interval, and therefore it's quite natural, you know, that you have to begin from epsilon n is here, yeah. So you know that you have to begin from 1 plus double from p plus epsilon which is very small, and the thing should grow to the value of the order of 1 here. What kind of function, okay, we can consider which would be reasonable? Of course, the most natural function for me is like this one. Some people, of course, can do like this one, but on the short interval also you can consider even functions which are not differentiable at each point. I can give you a couple of examples, but why so-called complicate life, especially if we want to approximate this function on a short time interval. Therefore, the generic parameterization, okay, for this deviation of equation of state from cosmological constant is like this one. It's some constant beta divided by n plus 1 in power alpha. You also can add logarithms here, logarithm n, but it doesn't change too much, but allows us to cover something like deep brain inflation, etc. And now you know that both alpha and beta should be of the order of 1. Beta should be of the order of 1 because at n equal what happened? Ah, okay. It's again collapsed. Yeah, so okay, it came back. Very good, and on the next page already. And then, after that, what you do? You just take this parameterization where you use two numbers about which you know that they should be of the order of 1, and try to extract what would be the observational consequences. Because in fact, in observations, we do not check too much. We are measuring 3 numbers. And when people say that, okay, some theory fits observation very well, if the theory has 20 parameters, I think it's not surprising. It would be surprising that it would not fit the observation. So, but here, what kind of predictions this model has? As you know, because I am using one fluid approximation, that is obvious that perturbation should be adiabatic, Gaussian, okay? And also, we have prediction for what people call spectral index, which I love to write in terms of deviation of equation of state from cosmological constant plus the rate of the change of this deviation of equation of state from cosmological constant. And you understand that 1 plus p over epsilon you can take very small, but you want to finish inflation in 70 e-folds. And this puts you some bound on the rate of change, because if this thing is very small, this thing should be very large, as we will see in a minute. And also there is the ratio of tensor to scalar perturbation, which is proportional to 1 plus p over epsilon, but here, as you understand, you can do this thing as small as you want because there is no second term. Let's see how it happens. In fact, if you would take this parameterization about which I told you that for deviation of spectral index, you are getting the quantity minus 3 beta, where beta was this, beta divided, okay, I will write 1 plus p over epsilon was alpha beta divided by n in power alpha. And there is the second term. First term is deviation of equation of state by itself. And second is the rate of change of the deviation of equation of state from cosmological constant. Then you see there are two numbers, but if you will take beta of the order of 1, as it should be, and we'll look at this ns minus 1 as a function of alpha, because alpha we do not know, n should be about 50, 60, yeah? So this is this uncertainty between a relation of the scale of inflation with the present scale. Then you will find that this function, 1 minus ns, as a function of alpha, has a minima. And this minima correspond to 3.2% deviation of spectral index from 1, at least. Therefore, generic conclusion, irrespectively, okay, what kind of model you are considering within this class of models, there should be more than 3% deviation of the spectral index from the flat one. And this is robust conclusion why actually we are insisting that generic inflation predict red tilted spectra with at least 3% deviation. Second thing, and by the way, this minimal deviation for n equal 50, you are getting for so-called logarithmic potentials in Debray inflation. And for which also the ratio of scalar to tensor perturbations, okay, is still within, how it's called, experimental curve. Now, if you would take, for instance, ratio of tensor to scalar perturbations, then you see that because of this alpha, you clearly can suppress it as much as you want. Because for alpha equal to, okay, this ratio is at least 50 times smaller than for alpha equal 1. And it's more or less natural thing. Second thing, if you would consider alpha larger than 1, then the first term in the first formula, which is on this transparency, becomes irrelevant. So deviation of spectral index from n equal 1 becomes independent on one of the parameters, and they are determined entirely by alpha divided by n. Now, if you would take now observational number 0.96, okay, with good accuracy, you see that you cannot have n equal alpha equals 3 from here, because if you would take alpha equals 3, if you want to suppress as much as you want, yeah, gravity waves, then you would get spectral index 0.94. Therefore, from here, it follows that given the value of spectral index 0.96, you are getting the low bound, okay, which is rather universal on the amount of gravity wave. And this universal low bound is more or less the same as in R squared gravity. You see? So you are expecting the amount of gravity waves at the level of 0.3%, because beta z is equal 1/3. And this is the things which actually in principle realistic, and it gives some kind of very good argument for going for next generation of the space mission, where people will be able to see these gravity waves. But it's somehow, it's perhaps because, right. So so you see that actually the hope for the gravity wave for spectral index 0.96 is not completely hopeless. If you would find 0.94, then, okay, the bound would go down by 50. And then, okay, I do not know what you have to do to get 50 times less even gravity waves. Now, other thing, of course, you could wonder how all this consideration is related with so-called fundamental scenarios, where you introduce scalar field, in spite of the fact that actually it's not quite clear that if everything is described effectively, do you need to map this scheme to some scheme related with scalar fields? But it's useful to do just to relate the things with which people were doing. And for that, let's take and map this kind of consideration to parameter dependence of deviation of equation of state from n equal 1 to the series of scalar field with different potentials. And you can do it, okay, let's don't go in these details of perturbation, of elementary calculations, because I promised 10 minutes more for lunch. Yeah, and let's go to the result immediately. Okay, how you can recalculate effective equation of state to the potential of the scalar field? It's in fact very easy. You just use conservation law for the energy densities, and you know that on inflation, potential is the same thing as energy density, so you find dependence of the number of e-faults, and then also using this kind of relation, you find the dependence of the number of e-faults on the value of scalar field, assuming that it's slow roll stuff. Now, then you see that there are two special cases for these alpha and beta parameters. Namely, you distinguish alpha equal 1, which is very special case, alpha equal 2, which is also a very special case. If you will take alpha equal 1, then you will see that you are getting the whole class of power law potentials, because then integrating this equation, you will find that potential in this case should be phi in some power, and power is determined by this beta, which of the order of 1. And then also, only in this particular case, both terms, first and second, first term, I mean term which is deviation of equation of state from cosmological constant, the second is the rate of change, contribute equally in the spectral index, deviation from n equal 1. And then, okay, playing with beta, you can get 0.96, 94, whatsoever, or 92, taking high and high potentials. But one of the problems here is that you are always getting, for the ratio of tensor to scalar perturbation, more or less the same thing. I mean, namely, a lot of gravity waves. So for phi squared, you know that it's 16%. For phi 4, it's 32%, etc., etc., etc. And here there is no way to reduce the thing. Therefore, it's, by the way, but it's a very special point in the class of all possible potentials. Second case, which is also very special, is the case when alpha equal 2. So in this case, deviation of spectral index are unambiguous, of course. They do not depend on beta, very essentially. And the amount of gravity wave is 50 times less. And this is more natural because, as we will see, the region between alpha 1 and 2, it also always corresponds to the reduced amount of the gravitational wave. But this particular case, alpha equal 2, correspond to exponent, or better to say 1 minus exponential potential effectively. And you can map this kind of theory either to R squared theory or to Higgs inflation or whatsoever. There is actually the whole class of the inflation which correspond to more or less the same potential in the relevant region. Now, what happens in between? There are three possibilities. Alpha is smaller than 1, alpha between 1 and 2, and alpha larger than 1. First of all, I want to say that alpha smaller than 2 correspond to so-called large field inflationary model, and alpha larger than 2 correspond to small field inflationary model, as you can infer from the previous formulas. Now, alpha smaller than 1, okay, it's exponent of this phi in some power, is out for sure, because it gives too much deviation of spectral index from n equal 1, and also it gives actually too much gravitational wave. But the whole interval, now alpha is larger than 2, is also out by observation. Why? Because it gives us too large deviation generically of spectral index from n equal 1, like 0.94. Therefore, the whole natural region here is in between alpha equal 1 and alpha equal 2. And if you would take, for instance, some generic point like 3/2 for alpha or whatsoever, then you are getting generically small amount of the gravitational wave at the level, as I said, yeah, I'm finishing, at the level, as I said, like 0.3%. Now, the question is, within this kind of simple models, can we still reduce the amount of gravity wave further? Answer to this question is yes, but not too much. Why? Because you could consider in principle as a free parameter what people call the speed of sound. It's in addition to the equation of state. In this case, the ratio of tensor to scalar ratio, okay, is suppressed by the speed of sound. But on the other side, you know that FNL is inversely proportional to the speed of sound. And from bounds of FNL follows the bounds on the speed of sound. Therefore, okay, you can perhaps reduce the things by factor few. Therefore, it will be not surprising if prism will not find the things at the level of 10 sigma, yeah? But not more. And in a sense, okay, there is this kind of low bound which is not very far away from what people actually are suggesting as an accuracy, projected accuracy for the next satellite, space satellite mission. Yeah. Okay, so this is all. Thank you.
Okay, questions?
Hi, Slava. So one thing, if suppose you don't see tensor to scalar ratio even below 1 part in 10 raised to 3, say, for instance, what will you say?
If I do not see below this upper low limit, okay, when I will not see, then I will tell what I.
No, but then how would it? Because you have set a lower bound here.
Yes.
So then what will be the implications?
The
Because you're
implication will be a complete catastrophe. But you know that in this case, okay, it's not tomorrow and not after tomorrow, it's in 30 years, okay, at least. And therefore, okay, I think about it, but not up to such extent.
And the second question regarding dark matter is that suppose if this inflaton starts oscillating during preheating, you will start ending up a lot more structures.
No, it's
Why?
actually, you see, inflaton is starting to oscillate, but nevertheless oscillation have nothing to do with distribution of the energy density of inflaton. So doesn't matter that it oscillates, but here, nevertheless, you have precise pattern for this kind of imitator of cold energy, okay, precise imitator of what you would get in a case of cold dark matter. Because in a case of cold dark matter, of course, inflaton decays, yeah.
Start forming structures even at the time of the reheating or preheating.
Well, I have no idea. No, why? Because actually the amount of this thing at the moment when you have graceful exit from inflation is negligible because it has to start to dominate at the moment of equality, as you understand. Therefore, energy density of this dust is by 25 orders of magnitude less than the energy density of radiation at the end of inflation. Yeah,
So you've added a scalar degree of freedom that behaves exactly like dust?
absolutely. It's not even scalar degree of freedom because you see, normally degree of freedom, as I say, it's the number of initial conditions divided by 2. Therefore, okay, there should be second order differential equation for the scalar field. But here is, you have first order differential equation. Moreover, it's equation which is similar to this Hamilton-Jacobi. It's some kind of
Exactly.
degree
So
of freedom
where
which
is
is
this
shared
difference?
by gravity and this scalar field. Yeah.
So where is this different from the scalar field that you use in, for example, the Seldovich approximation? Isn't it exactly this?
No,
So-
if it's potential, right?
Yes,
You consider then it's not different. But you see, the main thing here is that energy density. You see, you could write this thing, but then modify this equation like this one, and then you could add something like energy density here. Then there is no difference, of course, on practical sense. But you understand that this kind of stuff is not consistent. And what I wrote, when the role of energy density is played by scalar curvature itself, is completely consistent modification.
But since you have nothing like a sound speed or a viscosity at the forming of cusps, isn't that simply the fluid description breaking down and you need the particle description?
No. But there is no particles there. You see, the problem is that in this kind of approach, there is no particle. Gravity imitates itself what people, okay, normally refer to the particle. Because you know that gravity normally has 2 own degrees of freedom. It's 2 transverse degrees of freedom for the graviton. And longitudinal degree of freedom or scale factor is not normally own degree of freedom of the gravity. It's induced by the matter degrees of freedom, as you know very well. Yeah. And here, and normally in the absence of matter, it's absent. But here, even in the absence of matter, it's present because you can set, okay, t here equal to 0. And in a case of, for instance, spherically symmetrical case, you are getting Tolman solution. Just without adding any dust, without adding any matter. Because at the beginning, before, okay, we realized that everything is so simple, we solved a lot of problems just stupidly, okay, taking and solving Einstein equation for these modified equations. But then and then getting this extra constant of integrations.
Okay, so I have in fact 2 announcements before we go and run. First announcement is that there will be parallel sessions in the afternoon again. So if you haven't given your talk yet, please do that at the reception desk. There will be USB sticks. And then next announcement is that tonight, of course, there's the banquet. The banquet starts at 7 o'clock but I believe at 6:30 there will be drinks in Trinity. Is that, no? Am I making that up? I will double check.
At 5.
Drinks on me, but no. Okay, no, it starts. Okay, it starts at 7 o'clock. Okay, so let's thank Slava again for.